Okay, assessment. Oil GC projects. Sand unloading. And we could throw rocket basketball in there too. So that's all this same. You didn't create anything, but we did a lot of that in class. And integral. So that will be the assessment on Thursday. We'll cover that stuff. All the math that led up to the sand unloading activity. Questions on that? That will be Thursday. What's that? Nope, it'll just be a paper. Okay, so then we started talking about parametric functions. So, got your laptops? Get them out. Laptops. I'll show it again. I'll show that again. Okay, so open up a blank window. Okay, and I left the, in case you want to jot down what the quiz is on. So here's a graph that I've graphed parametrically. So I created this parametrically. Can you do it? Can you do it? So remember what is a parametric function? What is a parametric function? How does it work? Well, that's in GC how you get a vector for points, but what is a parametric function? What's that?
Goes off of the parameters of distance and angle as opposed to x and y coordinates.
I think you're thinking polar.
Oh, shoot. Yeah.
But that's a good answer for polar. All right, what about parametric? What did we talk about last time? Should we review that? Remember the caterpillar? Can the curve of the caterpillar be a function?
Yes.
But the curve itself, right? Can that curve be a function? That curve, can it be a function? How, that particular curve, that set of points, can it be a function? And if so, how? Right? Doesn't this fail the vertical and horizontal line test miserably? So how can it be a function? How can that curve be a function? Who remembers? Jessica, you're trying to answer, right?
Sure. So you can think of each individual point on the line, because that's what a graph is infinite number of points.
Okay.
So each point has an x and a y coordinate.
Right.
So we can use it as a function of t's or just whatever parameter we want to use.
So
and each
independent variable is
t,
t, and the dependent,
or x and y coordinates is a function of t.
right. So if this is how we think about the independent and dependent quantities, as the independent is some parameter t, and the dependent is what? Location in the xy plane based on t, is that a function? And why? Why do we say that is a valid function? Peter, why? So why is that a valid function?
That one t value you're always going to be each t value has only one. So like x, y,
Right. Given any t, you only get one xy back from every t. So this is the idea of a parametric function, right? So a parametric function is that x is some function of our parameter, and y is some other function of the parameter. And so now the output or the dependent is this ordered pair of x and y together. And so any given point, given any t, you only get 1 point on that curve. So then I told you that in GC, if you hit Control 2, and we use that for points, right? So, and that's a good way to think of this parametrically, because what is a parametric function? What is any function? Set of points, right? And so using what we used before as the point makes sense, right? We're saying xy represents a point, and how are we going to get those points? By whatever our function of t is that gives the x coordinate, and whatever function of t is that gives the y coordinate. So those two individual functions of t put together make this parametric function, giving us ordered pairs, which gives us points, right? So these are points. So how are we doing? Did we get it? So what happens is, so we have to tell what the domain then is values of t, right? The domain is values of t, and so to set the domain, it's in the upper right hand corner. It's really small. So it's really small up there, and you can change what t starts at and what t ends at.
If that doesn't pop up for us,
It should be there somewhere.
it's on the bottom right. Oh, okay. So
Okay, you near graph. So you got to hit graph. Hit enter to graph it, and then it pops up.
I know. Like, because I don't want to write on my. Oh, so you have to do it before my list. Oh my gosh.
Okay, is everyone there or getting help to get there? Okay, so now notice I'm showing from 0 to 2 pi, right? I'm showing from 0 to 2 pi. Is that what you're showing? But look, did yours start out at 1? 0 to 1? And is that what you got when you had 0 to 1?
No.
Okay, so I'll make it work for 0 to 1. So I want to get the whole circle, not just the part from 0 to 1 radian. I want to get the whole circle when t goes from 0 to 1. So make that work. Okay, questions?
How come yours did both?
Because if it does it for 0 to 1, it's going to do it for 0 to 2 pi. It's going to go, just go further.
You just keep straight.
It's going back on
It's going to go back on itself.
Oh.
Yeah.
Already?
Actually,
So we're going to make it work from 0 to 1. It's going to make it work from 0 to 2.
Watch out, guys. First I did 8. Look, I tried 8 too. Yeah, I did it for fun. Yeah, it's like
Okay, so lots of you are kind of just repeating what I wrote, and so you just go ahead and put the function, the rule in here. Okay, so it's just using up command lines that you don't need to use up. So just go ahead and put your rule right there. That's the way we normally do it instead of. So we do want to employ lots of functions, but that's kind of overkill. It's kind of overkill. You just put the rule right in there. Okay. Any questions? Do we get it? So if we want it, so what we think of 0 is going to match up with the starting point, and then if 1 matches up with the ending point, then how do we adjust that function? Let's see. Sing, did you get it? Did it work? Okay, tell me what you did. Okay.
Yeah. It's just starting here. Cosine literally is horizontal. Horizontal distance.
Oh.
Or your x.
Okay, so I just zoomed in on the x-axis. And so my question to you is it a circle? Is it a circle? Sure doesn't look like it. Right? So is it a circle or not? Yes. Okay. So you're still saying yes. Then prove it. Prove it that it's a circle. You guys are in lots of upper division math classes where you're doing proofs, right? So prove that it's a circle. Mathematically, give a proof that it's a circle. Because visually, it sure doesn't seem like a circle, right? What are we talking about? To prove that it's a circle, it's about what? Distance to the center, right? So, Jose, you want to put it on the board? Sure. Can you explain what you did?
Which floor?
Sure, back there is great. In the words of my son, Papa, Papa. Oh.
Alright. Yeah, no. Okay. So basically figuring out distance from 0, comma 0 to cos 2 pi t, comma sine pi t. And so you just put these points in the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. And so that becomes square root of,
Don't write -0.
okay, cos 2 pi t, and then you would have -0, but so don't need that. And so since that's -0, you just have cos squared 2 pi t
Right.
plus sine squared 2 pi t, and then you use the property that that cos squared x plus sine squared x equals 1, and so this equals square root of 1, which equals 1. So no matter what t is, you're 1 away from the origin.
Well done. Okay, so is it a circle? Hold on. Is it a circle? Okay. Graph it. Graph it by altering the function you already did. So go ahead and if you find f of t and g of t, get rid of that and just do the one line version of the circle, and then graph this by altering the graph of your circle, or altering the command line for your circle. Okay, got it? What did you do? You took all the x coordinates times 2 and all the y coordinates times 2.
The square root of all that equals the hypotenuse?
So you got a new circle. Don't mess with the math anymore, it'll confuse you, so get your scale even on both ends. Now we're actually not in a circle. So all you did, so what you do, you took all the x coordinates by 2 and all the y coordinates by 2 and just made a bigger circle. So what did I do to get that ellipse? You get it? Everyone get it? Yeah. Okay. So what do we have now? It is an what? an ellipse, okay? So we have this set of points. Oh, shoot. I'll just go like this. So you should. So what happened? We just took all the x coordinates of those points and made them twice as great. So that's gonna take all those points and move them out, stretch them out times 2 horizontally. Okay. So you told me that these set of points is an ellipse. So given that set of points, prove that it's an ellipse.
So for an ellipse.
So do we have an equidistant property here?
Yeah, from two foci, oh gosh.
But we need every single point the whole set of points to be an ellipse.
Right, so the rule for the ellipse.
So what do you know what an ellipse is centered at the origin? Anybody remember? Someone's saying it. Who's saying it? Who was saying it?
Divided by like two different radii.
X squared. Okay, so we won't do this now. This will be part of the next homework assignment. So proving this is an ellipse isn't about equidistance anymore, right? Because every point is a different distance from. Yeah. So every point is a different distance from the origin. So you can't do that. But if we know that this is the equation of ellipse, given this set of points right here, can you show that it has this form of a relationship of x and y? So what does it mean? It means eliminating t. Again, just like in the distance formula, t was eliminated and we saw every distance or every radius was 1. So now it's about given our set of points defined this way, does it hold this relationship of x and y? That would be a proof that it's an ellipse. But like I said, that's just a precursor to a homework problem. Okay. Any questions on that exercise? We're not going to work on it now. Okay, so something else here. So I want us to use something we learned. Notice what my t-value is. What's my t-value? From what to what? 0 to 1 still. 0 to 1 still. So we, a while back, learned something that could help us easily do this. So if you remember what we learned, you don't have to do a bunch of scratch work to figure out how to make this work. You could just apply this thing that we learned, and you can kind of just type it in and get it. So do you remember? Maybe you can discuss at your table. What was it that we learned? T varies from 0 to 1 that could give me this set of points. Talk about it. See if you remember. Someone at your table remembers. Someone at your table remembers. Remember, it could be applied to anything. That was the whole point of that. Values, points, functions.
When he remember when we made that graph into the other graph, the sign graph turned into like a vector graph. Oh, and it looked
It like melted down to my finger. Okay, I don't remember what it did though. Wait, what day did we do that? What was
Okay, so when t equals 0, so I'm going to say cosine of an argument and sine of an argument. When t equals 0, we want the argument to be what? Pi over 4, right? Pi over 4. And when t equals 1, we want the argument to be 3 pi over 2, right? 3 pi over 2 at the bottom of the circle. So what construct that we talked about, if you can remember what it was. So when you plug in 0, you want it to spit out pi over 4. When you plug in 1, you want it to spit out 3 pi over 2. You kind of remember it enough to kind of figure it out. That's the thing. Did you remember it? Did it work? Okay, well, you got it? So remember it? No.
No, it's not. Yeah, let me see. But I have one. It just.
But you're not using, we want to use 3 pi over 2 and pi over 4, right? So, so we want to figure out what that construct is that uses these. So yeah, you got it in there, but you're doing some math to simplify it. Does anybody remember? Remember the parabola morphing into the cosine function?
The visual was too cool. We didn't remember the real point.
Arg. Is that for argument or is that for arg? You don't remember.
Wasn't it like there was a 1 minus?
1 minus, okay.
And there was one big
So let's see if we can do it as a class. Genevieve said 1 minus.
1 minus t.
Joey.
Yeah, 1 minus times g of x plus. Oh, I guess what are we using?
No, but we want to get from t values to angles. So it's not going to be n. It's not going to be any functions. We want to get from t values to angles.
Yeah, so that's why instead of 2 pi times 2 pi to the whole circle, it goes 5.
So 1 minus t. So when we plug t equals 0 into this, so think about what happens when you plug 0 into 1 minus t. What happens when you plug 1 into 1 minus t? Okay, so this is a little hint. It has to do with 1 minus t. So what happens when you plug 0 into 1 minus t? And how can that help you get what? Pi over 4. And what happens when you plug 1 into 1 minus t? How can that help you get 3 pi over 2? Put your heads together. Finish this. So this is part of it. 1 minus t is part of it. So what you wanted to be able to change one function into another. So it's general principle. So what we want to do now is we want to show all the points between the starting angle and the finishing angle. So then in functions you have angles, right? So here you have a starting function and an ending function. So here you have a starting angle and an ending angle, right? And instead of doing it one point at a time, as n does, do it all at once, which is what t does, right? It's all What happens when you plug 0 into 1 minus t? What do you get?
Opposite.
1. So, and what do we want when t equals 0? Pi over 4. So where should I put pi over 4? If I plug 0 in, then I'm going to get 1. So that means I want to get pi over 4 out of this, right? So where should I put pi over 4? Here, right?
Ooh, that's what this is. This is pi over 4 and this is 35.
Now when I plug 1 in, what am I going to get? To that. 0, which says pi over 4 doesn't have an effect anymore. So then I need something to get the 3 pi over 2. Plus 3 pi over 2 times? And does that still work when t equals 0? Does it still give me pi over 4? Yes, because now that goes away. If t equals 0, 3 pi over 2 is gone, and I get pi over 4. When t equals 1, pi over 4 goes away, because it's times 0, and we'll get all 3 pi over 2. And then in between, we get every linear value in between. So now finish it. So keeping t from 0 to 1, graph this set of points. What does it give you? For values of t, what does this give you? What quantity does it give you for different values of t? When you plug a value of t into this, what does it give you? Angle measure, okay? Right, and when t equals 0, it gives you the angle measure pi over 4, and when t equals 1, it gives you the angle measure 3 pi over 2. Yeah. Okay.
This is what I originally had, and then just
Right.
about to change it to what we have. But I'm confused on why. What's the difference?
Well, so if you change this around, what you see, you get 3 pi over 2t
Yeah.
minus pi over 4t, and then plus pi over 4.
Yeah.
Yeah.
I'm just wondering
Well,
like
this
why.
is very convenient because you don't have to do any thinking. You don't have to do the math that you did. You see, so you did some calculations to get
Right.
that.
Well,
So this is if you were to do this over and over and over again, you don't want to do those calculations over and over and over again. You just want to plug in the endpoints.
right.
If you want to repeat this, it makes it a lot more convenient because it's one end to the other.
So what this,
I just don't get the conceptual like side of like what you're doing there, because like the way I wrote it, like that made more sense conceptually in my head, but it's not.
So like a month ago we
Yeah.
investigated it. So do you see at t equals 0 that you get 3 pi over 2?
Yes.
Or sorry, pi over 4.
Yeah.
Okay, when t equals 0, this goes away, and then you get all pi over 4. And then when t equals 1, what do you get? 3 pi over 2, right? So this all goes away. So as t changes from 0 to 1, you're linearly changing from, in a linear fashion, you're going to gradually change between pi over 4 to 3 pi over 2 as t goes from 0 to 1.
I like test a point in the middle to see
Yeah.
that it's equal. So this is kind of a way of like scaling cosine domains, but like a range of t values to any beginning point and end.
Right, 0 to 1. Always take 0 to 1 to a linear span, I guess, from your starting value to your finishing value.
How much does directionality matter? Like if you did pi over 4 times 2 and then 3 pi over 2 times 1 minus t, I mean you just go like range from 0 to
So that's the thing about parametric functions. They have a direction, right? So this, the way I've done it, is going to have this direction. It's going to go counterclockwise.
right. Do you want it to go? I mean, you did that
It's just you should know that there is direction to it. I don't want anything right now. There's nothing that I want, but just to create this set of points. But just, know that if you switch these, t going from 0 to 1 is going to generate the points this way.
That's inconsequential.
For this exercise, yeah.
So if you were to do times 4 times 2 minus t instead of 1 minus t, when you add a 3 pi over 2, you have to do t minus 1. Like if you want to go from 0 to 2, instead of 0 to 1.
Okay, to get the same, so if you want t to 0 to 2, then you do 2 minus t.
And then what would that t do?
You get the exact same set of points.
That is, well, it's still 3 pi over 2 times t. Like,
Wait,
the only thing that would change is that one, is private ones goes to minus D.
Yeah, because if you plug into equals 0, you're gonna get. Oh no. That's,
It doesn't work.
yeah, if you plug in 0, then you're gonna get 2 times pi over 4.
Right, so it only works for going from 0 to 1.
0 to 1, right?
Oh, yeah, so then.
I always go back to the pi times 0.
And if it were 0 to 2, you choose the 1 to 2.
No, that's
Okay, so remember that this thing, so here we're using it for angle measure, okay? We used it for functions, right? We used it for functions, morphing one function into another, right? We used it just for just values. We saw it for points. We could do, so remember if we said, like say, 5, 3, do you remember what that did when we put a line like that? Gives all the points on the line between the 0.53 and 2, -4. So this is a versatile thing. Like it can be used for functions, values, points. In this case, we're using it for angle measures. Okay. Okay, anybody have a question? Did it work? Were you able to now graph this using that thing? So especially when you're creating animations and you're doing something like this over and over and over again, it just makes it really convenient to have a form like this. And so suppose I want to graph several curves, and I only have one choice for where t can start and stop, right? So say I want to graph that curve, and then I want to graph in the same plane, I want to graph a circle of radius 2 from 3 pi over 4 to 9 pi over 2. So do that. So now in the same plane, graph circle radius 1.5. So we'll do 1.5. But only the part that goes from, what did I say? 3 pi over 4 to 8. 9. What is the top of the circle? 5 pi over 2. So in this same plane, so simultaneously now graph the circle of radius 1.5, starting at 3 pi over 4 till 5 pi over 2. And you can leave t from 0 to 1, and then we'll graph both of them. Okay? So go ahead and do that. In the same window pane, now graph that part of the circle of radius 1.5. And a hush fell over the crowd. Okay. So this is the idea here that so we can keep t from 0 to 1. We can graph all kinds of things, keeping the range of t the same. We can graph them all the same by using that convenient construct that we're talking about.
We could make a maze.
What's that?
We could make a maze.
Yeah, you can make a maze. That's right. Circle maze. Okay, so the next GC activity that you have relates to this. And so this is the generalized parametric. And so what I have there, I'm graphing the function cosine x plus 1. And that's the purple one, but I could change that. So it could be, 2 sine x plus a half. All right, and then gx, right now I have e to the x minus 1. I could do negative a half x cubed along with that, say. Does it show something? Okay, good. And then notice I have these these sliders LF, RF, LG, and RG. So LF is the left side of the interval I want to show F, and RF is the right side of the interval I want to show for F. So I'm changing, by changing left of F, it changes where the interval at which it's being shown.
It's just doing integers.
Yeah, I've got it set at integers, yeah. Negative 5 to 5. Okay? And then similarly for LG, I can start the left side anywhere I want, and then end it on the right anywhere I want. Okay, but notice what the name of this is. What is the name of this project? Generalized what? Parametric. So students have done this and have totally ignored the instructions and got a associated grade with that. Okay, this is about parametric functions. You're graphing f and g parametrically. Okay. Okay, so please hear me now. This is about applying what we've learned in class today. So that's the goal of this assignment. So you've got your assessment for Thursday, so we'll make this due Tuesday, okay? We'll make this due Tuesday. Yeah, questions about this?
Yeah, I'm sorry, is the piles in the T's? Where do the T's come in?
What's that?
Where do the T's come in?
When you graph them.
You have to do that part.
So this is just defining the function, right? So the function f is this just defines it. X is not the x-axis. It's just a dummy variable. See, this isn't graphing. This is just defining the function. And this is just defining the function. You're going to graph them using parametric. Yeah. You're going to graph these functions parametrically. And then also, you need the sliders that adjust the endpoints, okay? So this whole thing can be done applying things we've learned today. That's the goal. Apply what we learned today in class.